Swayam Prabha. Digital India. Educated India.
Welcome to the class. Last time we had seen some examples on Rankine cycle with reheat or maybe regeneration, and also the example for the back pressure turbine or cogeneration plant. Today we will continue with similar example, but we will also see the example for binary cycles. So let us see our first example. Our first example reads that there is a single reheat regenerative cycle of steam where steam enters the turbine at 30 bar and 400 degrees Celsius and the exhaust pressure is 0.1 bar. The feed water heater is a direct contact type feed water heater which operates at 5 bar pressure. Find out efficiency and steam rate of the cycle. We know steam rate means specific steam consumption, SSC, and increase in mean temperature of heat addition, efficiency and steam rate as compared to the Rankine cycle without generation. We are supposed to neglect the pump work. Let us feel this would be our possible TS diagram. So in this TS diagram, what we are given with? We are here given with the fact that T5. So here we will see whatever it is given to us as per this diagram. We are given with T5 and that is equal to 400 degrees Celsius. We are also given with P5 is equal to P4 is equal to P3 and that is 30 bar. And then we are given with P1 is equal to P7 is equal to 0.1 bar. So these things are given to us. We are said that P6 is equal to P3 is equal to 5 bar, and we are said that it is a direct contact type feed water heater. Since it's a direct, we are knowing that 0.3 will be a saturation point, and then we know that M1 mass which is bled from the turbine is losing its enthalpy from H6 to H3, and that is giving rise to the enthalpy for 1 minus M1 steam which is pumped to pressure H2, but it is rising its enthalpy from H3 to H2. So these things are given to us. So now let us work with this example and find out whatever it is told to us. So first we know now HP5 is known to us. We know T5. We will go to the steam table. We will go to the saturation part of the steam table, and then we will know the enthalpy which is H5 is equal to 3230.9. Then we have to find out 0.6 which is at 5 bar. So for that we will take entropy's help from 0.5. So we know at the same part in the steam table which is saturation, supersaturated part or superheated part of the steam table corresponding to 30 bar and 400 degrees Celsius, we find out entropy S5. But this S5 is equal to basically S6 and S7. This S5 is equal to S6 and S7. Knowing this, we can find out what is the SG corresponding to 5 bar. That means we are trying to see what is the entropy here. And so this entropy is 6.821, but we know S5 is 6.9. So basically S6 is greater than SG, that means T6 and H6 are to be found out from the superheated part of the steam table corresponding to 5 bar, and that turns out to be T6 is equal to 172 degrees Celsius and H6 is equal to 2796 kilojoule per kg. Then we can also take use of S7 is equal to S5. So S7 is equal to SF at 0.1 bar, which is this basically S1, and X7, that is dryness fraction at 7 into SFG, the total change in enthalpy due to phase change at 0.1 bar. Then we know X7 is equal to 0.836. This would be helpful to find out H7, since H7 is equal to HF at 0.1 bar plus X7 plus HFG into X7 into HFG at 0.1 bar. So this is our H7. This HF is known at 0.1 bar, HFG is known at 0.1 bar, X7 is known from the previous step. So this is how we evaluated our H7. Now we can know what is H1. H1 is 0.1 bar saturation liquid enthalpy, and then that is equal to H2, since we are supposed to neglect the pump work. So H1 is equal to H2 is 191. We are also taking help to neglect the pump work, where H3 is equal to H4, and then H3 is also known to us. Then as what? Since direct feed water heater is given to us. So this is the formula which we were knowing. From that we can find out M. Since H6 is known from previous step, H3 is known as a liquid saturation enthalpy, H3 is known, and we know H2. So knowing all these things, we can find out M. Then we can find out turbine work. So for turbine work, we know that 1 kg of steam is expanding from H5 to H6, and 1 minus M kg of steam is expanding from H6 to H7. So we have formula which is 1 into H5 minus H6 plus 1 minus M into H6 minus H7. So turbine work turns out to be 916.13 kilojoule per kg. Then we know formula for specific steam consumption or steam rate, which is 3600 divided by W net. But W net doesn't have pump work. So WT, and that turns out to be 3.93 kg per kilowatt hour. Then we can find out Q1, which is heat addition from the external source, that is H5 minus H4. This is 2590.67. So this helps us to find out cycle efficiency, and this is 0.3536, which is basically W net upon Q in, and W net is equal to WT and Q in is equal to Q1. Then this example is continued. We can find out mean temperature of heat addition. Mean temperature of heat addition for the cycle without heat addition and for cycle with heat addition. So mean temperature of heat addition is basically T with regeneration is here H3 minus H5. H3 minus H5 divided by S3 minus S5. This is mean temperature of heat addition with regeneration, and without regeneration is basically H5, H1, H5, we have basically mean temperature of heat addition as H5 minus H3 divided by S5 minus S3. This is with regeneration, and without regeneration we have H5 minus H1, H5 minus H1 divided by S5 minus S1. So this gives us the mean temperature of heat addition to be 238.8 with regeneration and 211.4 without regeneration. So this is giving us that mean temperature of heat addition has increased by 27.4 degrees Celsius due to regeneration. So turbine work without regeneration is 1 kg of steam has completely expanded from state 5 to state 7. So it is 1038.7. So steam rate is 3600 divided by turbine and work, and that is without regeneration it is 3.46 kg per kilowatt hour. So increase in steam rate is 0.476 kg per kilowatt hour, and efficiency of cycle is basically without regeneration it is H5 minus H7, that is turbine work, divided by heat addition, which is H5 minus H2, and this is 34.18. But efficiency with regeneration has increased by 1.18%. So this is how we would have solved this example for the regeneration case. Now we will move on to the next example, and next example says that mercury cycle is supposed on there is mercury cycle which is supposed on the steam cycle. So mercury cycle is given as a topping cycle, and water cycle or steam cycle is given as a bottoming cycle, where there is heat exchange between boiler outlet condition at 40 bar and 400 degrees Celsius and the condenser as 40 degrees Celsius. So the boiler for the steam is given as 40 bar and 400 degrees Celsius, and condenser for steam is given as 40 degrees Celsius. The heat released by mercury condensing at 0.2 bar is used to impart the latent heat of vaporization to the water in the cycle. So it is told that only latent heat of vaporization is given by the topping cycle to the water, and that is mercury is doing condensation as at 0.2 bar. Mercury enters the mercury turbine as saturated vapor at 10 bar. Compute kg of mercury circulated per kg of water. Efficiency of combined cycle, property of mercury is given to us. Knowing this is our diagram, which states that we have water as the bottoming cycle and mercury as the topping cycle. We are given with the fact that P3 is equal to P2 is equal to P5 is equal to 40 bar. We are also given that T5 is equal to 400 degree Celsius, and we are told that the pressure is such that the temperature, which is T6 is equal to T1 is equal to 40 degree Celsius. So these things are given to us. So knowing these and also the conditions for the steam and the conditions for mercury, we can solve this example. So initially we can say that H5, we will go to the steam table, which is a saturated part, superheated part of the steam table. We will go to 40 degree bar and 400 degrees Celsius and find out H5. So H5 is known to us. For H5, from H5 we will also see in the steam table what is S5. So S5 is known to us, but S5 is equal to S6, but S6 is equal to SF plus X6 into SFG. So from that we can find out X6. So X6 is equal to 0.8064. Then we know X6, so we can find out H6. So enthalpy at the exit of the turbine. Then we also know H1. H1 is equal to 167.57. We also know H2. So here we are doing the addition of turbine work, pump work in H1. So H2 basically is equal to H1 plus the turbine work and pump work, and pump work. So this is H1 plus pump work, and pump work is V1 into delta P. So delta P is the pressure difference between P2 and P1. P2 pressure is 40 bar, P1 pressure is the pressure corresponding to saturation pressure at 40 degree Celsius. So this turns out to be 171.6 kilojoule per kg. Further, we wanted to know H3 since heat exchange is given, which is latent. So H3 is equal to the saturation liquid enthalpy corresponding to 40 bar. This is known. Further, H4 is known, that is saturation enthalpy of vapor corresponding to 40 bar. So we know HC. HC is given as the data corresponding to 10 bar. So mercury at higher pressure is 10 bar. So for 10 bar, we know what is Hg. So this is given to us, that is 363. So SC is entropy at C is given to us. This is entropy is given to us as this, and this entropy is equal to the SD, and SD's entropy can be found out as SA plus XD into SFG. So SFG is given to us, which is SG minus SF. So SG minus SF. So these all things are given, so we can find out XD, and this turns out that XD is equal to 0.7751. So HD can be found out by adding HG plus HF plus X into HFG, where HFG is Hg minus again HF. So into XD. So this is our HD. So then we know HA is equal to HB since we can neglect pump work. This gives us the formula for mass flow rate of mercury or fraction of mercury required per kg of steam flow rate is equal to H4 minus H3, which is latent enthalpy rise for the steam, divided by the heat rejected by the mercury, which is HD by HA. So knowing all the enthalpies, we can find out M, and that is 7.4159 kg of mercury per kg of water. Further, heat released in the heat added in the boiler is total amount of heat, where we have M amount of mercury is rising its enthalpy from HB to HC. So here in the mercury's boiler we are adding heat. Then we are also adding heat in the economizer of the steam and superheater of the steam. So economizer of steam will have enthalpy rise from H2 to H3, and economizer will have, superheater will have enthalpy rise from H4 to H5. So we have total heat addition 3733.1. We have total heat rejection, which is H6 minus H1. So we have combined cycle efficiency as 1 minus Q2 upon Q1, which is 48.9%. So we found out all the things whatever required for us in this example. So let us see our next example, and our next example says that in a combined gas turbine steam turbine power plant, the exhaust gas from open cycle gas turbine is the supply gas to the steam generator of steam cycle at which additional fuel is burnt in the gas. So it is told that exhaust of the gas turbine is first heated by burning extra fuel and then supplied as the flue gas in the boiler of the steam power plant. The pressure ratio of the gas turbine is 7.5, and air at the inlet is having temperature 15 degrees Celsius, and maximum temperature of the gas turbine is 750 degree Celsius. Combustion of additional fuel rises the gas temperature to 750 degree Celsius, and the gas leaves the steam generator at 100 degree Celsius. This data is also corresponding to gas turbine cycle. So we have given all these points. Then the steam is supplied to the turbine, which is steam turbine, at 50 bar and 600 degree Celsius, and this steam condenses to the pressure of 0.1 bar. Total power output of the plant is 200 megawatt. calorific value of the fuel burnt is 43.3 megajoule per kg, neglecting the effect of mass flow rate and fuel on the airflow, determine the flow rates of air and steam required, the power output of the gas turbine and steam turbine plant, thermal efficiency of the combined plant and air fuel ratio. We are given that Cp of the fuel, Cp of the gas is 1.11 kilojoule per kg and gamma of gas is 1.4. So, we are first going to find out what is the TS diagram. So, our TS diagram would look like this, where we have bottoming cycle as water and topping cycle as gas. We are given with T3, which is 750 degrees Celsius, and T5 is also 750 degrees Celsius. We are given with P2 by P1, which is pressure ratio, and that is told to be 7.5. So, knowing this information, we can work out with the gas turbine cycle. So, T2 by T1 is equal to P2 by P1 bracket raised to gamma minus 1 upon gamma. This is the isentropic relation, since it is a compressor. So, in the compressor we are having isentropic compression from the inlet condition. So, knowing the pressure ratio and knowing the temperature T1, we can find out T2. So, T2 is 512.165 Kelvin. Then similarly from the same pressure ratio we can find out T4. So, T4 by T3 is equal to P4 by P3 bracket raised to gamma minus 1 upon gamma. Here as well T3 is 750 degrees Celsius, P4 by P1 is known to us as 7.5. So, we found out T4 as 620 Kelvin. Then we can find out Hc. Hc is the enthalpy at the entry to the steam turbine, and this enthalpy can be found out from the superheated part of the steam table corresponding to 50 bar and 600 degree Celsius. Then we know Hd, since Sc is equal to Sd, entropy at C is equal to entropy at D, and entropy at C can be found out from steam table 50 bar and 600 degree Celsius. Then we can go to the lower pressure, which is 0.1 bar condenser pressure, and then from that Hf plus Xd into Hfd. From that we can find out enthalpy at D, but for that we need what is the dryness fraction at D. So, for that we are going to equate the entropy at C and entropy at D and then find out dryness fraction. So, knowing this, we can as well equate HA is equal to HB. We are supposed to neglect the pump work as given in the example. Then we can find out what is the net work in the gas turbine. Net work in the gas turbine is turbine work minus compressor work. We cannot neglect compressor work, since as what we had discussed in one of the classes, work ratio of the gas turbine cycle is low. So, compressor and turbine works are very high. So, we cannot neglect compressor work. So, for the net work in the gas turbine, we have turbine work minus compressor work. So, turbine work is T3 minus T4 into m dot A, mass of air, into Cp of gas, minus m dot A into Cp of air into T2 minus T1. So, we actually know these quantities, and then from that we can take the gas turbine work is equal to 221.47 into MA, which is mass flow rate of air, and that is not known to us. Steam turbine work is equal to mass flow rate of steam into Hc minus Hd. Basically, there is a mistake. So, the work done by the steam turbine is m dot S, mass flow rate of steam, into Hc minus Hd. So, we know Hc, we know Hd, so we can find out it is as 1367 into mass flow rate of steam. But we know that steam turbine work plus gas turbine work is equal to total work done, and that is given to us as 200 into 10 to the power 5, that is 200 megawatt. So, we know also that mass flow rate of air into Cp of gas is equal to T5 minus T6, T5 minus T6. This is the heat lost by the gas turbine to the steam turbine, where steam turbine is getting the heat from Hc to Hb. So basically it is rising its enthalpy from B to C. So this is the second equation. So this is equation number 2. So we know two equations and we know two unknowns, which is m dot A and m dot S. So we can find out first the ratio of m dot A by m dot S from this equation, which is now equation 2 for us, renewed equation 2 for us. Then this we can put over here, and then we can find out m dot A is equal to 398.34 and m dot S is equal to 81.9 kg per second. So we found out mass flow rate of steam and mass flow rate of air. Further, so we found out what is the steam gas turbines network and what is the steam turbines network. So these two also are found out. Then we will continue with this example. So we know that now Q1 is the heat received in the gas turbine, and gas turbine is receiving heat twice basically. One is during its combustion chamber and one is before passing it to the boiler. It is also getting heated from 4 to 5. So first heat addition is T3 to T2. T2 rise in temperature from T2 to T3, and second heat addition is rise in temperature from T4 to T5. So these two heat additions are for the gas turbine. So knowing this all quantities, we can find out Q1 is equal to 400.19 megawatt. Then efficiency of gas turbine power plant is net work upon turbine work, and that turns out to be 550%. So this is, we would have found out our net, this is the total network of the cycle, combined cycle. This is not the efficiency for the gas turbine power plant, this is the efficiency of combined cycle. So this is the network of the combined cycle, and this was given as 200 megawatt, but heat supply is basically only in the gas turbine. In the steam turbine we are not giving any heat. In last example where steam cycle were coupled, there we were only having heat exchange in the latent part for between the topping and bottoming cycle, but now we are having gas turbine as our cycle, where complete heat, which is HB to HC, was given from the gas turbine. So there is complete heat exchange between two cycles. There is no external heat added in the bottoming cycle. So we have only external heat addition in the topping cycle. So this turns out to be the efficiency for overall cycle. So W net upon Q1, and that is 50%. But Q1 is equal to mass of flow rate of fuel into calorific value of fuel. So that is MF into 43.3 into 10 to the power 3 kilojoule per kg of fuel. So this is MF into 43.3 into 10 to the power 3, that is kilojoule per, this is kilojoule, not per kg of fuel. This is kilojoule. So this is the heat supplied by combustion by the fuel, and this is heat received by the air. We are not assuming any loss. So heat rejected due to combustion or heat released in combustion is heat supplied in the gas turbine. So that equated would give us mass flow rate of air divided by mass flow rate of fuel as 42.7. So we need 42.7 times more air for the combustion of fuel in the gas turbine. So knowing this, we know now how to solve the example for the combined cycle, which is gas turbine, or also for the gas turbine and steam turbine cycle. We have also seen the examples corresponding to the reheat, regeneration, superheating. So how the concepts which are known to us from the basic theory of steam turbine and combined cycle, we are now eligible to solve the examples, and we have illustrated how to solve the examples. So, we will see the next part, which is now our steam turbine part, from the next class. Thank you.